In our previous class, we had an introduction to the EM algorithm. Today, we would be seeing an application of EM algorithm in R. The application of EM algorithm in R would be used in context to finding the missing values for a univariate normal distribution. So, basically what we would do is we would write a function in R that computes the mean and the variance for a univariate normal distribution when some of the values are missing. We would write a full function on the EM algorithm, but since it would be a long function, so we would be writing the function not in R per se, but we would be writing it in the slides, and then we would be calling that function in R to see what are the outputs. Objective. The objective here is to develop an EM algorithm for univariate normal in R. This code has originally been taken from the given website, but this has been a little bit modified to suit our needs. So, we start by creating a function called em.norm. Now, em.norm is a function, and this function takes three things. The first is the vector of inputs of the data, and by this is denoted by y, and this y contains both the observed as well as the missing data. Then we have MIT, which is the initial value for the mean which the user should provide, and we have SIT, which is the initial value of the standard deviation which the user should provide. What is the objective here? The objective here is to provide or to estimate what is the mean and what is the standard deviation for a univariate normal distribution having some missing observations. So, now comes the body of the function. So, in the body of the function, we have the vector y. So, we first generate two sub-vectors. One is y observed, that is y OBS, which is all those values for which the entry is not NA, and so this is given as not is dot NAY. So, it gives all the values for which y has a numeric value, and y miss are all those observations for which y is NA. And then what do we find? We find n, which is the total number of observations for y, and r, which is the total number of observations which are available. So, that is the length of y observed. Now, we set the initial values, and the initial values are MUT, and by default the MIT value is passed to the argument MUT, and SIT by default the initial value is passed to the initial value of the standard deviation is passed to SI. Then what do we have? We define the log likelihood function. So, this is the standard log likelihood function for a univariate normal, and this is defined in a function within the function em.norm, and that is LL, which is function y mu sigma square sigma 2, that is the sigma square, and n, and then we have the definition of the log likelihood. So, LL is a function which computes the log likelihood for a given mu sigma square and n. Now, after this we compute the log likelihood for the initial value. So, here the mu is replaced by MUT and the sigma square is replaced by SIT. Now we start the E step. So in the E step we have to write two E steps, one for Ey and one for Ey square. So that's Ey is sum of y observed plus n minus r into MUT. That's coming from our initial results in the last class, in the last session. And then Ey square is sum of y observed plus n minus r into MUT square plus SIT. Once we have defined Ey and Ey square, so once the E step is complete, we go to the updation step or the maximization step, which is the M step. And then in the maximization step, we replace the MUT by MUT1, or rather we have a new value of MUT1, which is Ey by n, and SIT1 is Ey square or Ey2 by n minus MUT1 square. And now we update the parameter values. How? By replacing MUT by MUT1 and SIT by SIT1. Once these are replaced, we can find what's the log likelihood of the current values. So then that becomes LLT, which is LL y observed MUT SIT n, and then we can print what's the value of MUT, what's the value of SIT, what's the value of LLT, and the slash n is for a new line. So this is kept under the repeat step. So when this is kept under the repeat step, that means that this particularly E step, creating the E step and the M step and then updating the parameter values is going on repeatedly till convergence. Then we have to add in some convergence values. So how do we add in the convergence values? We say that if the difference between the previous log likelihood and the present log likelihood, that is the absolute value of LLTM1 minus LLT, is less than 0.001, then we stop the computation by mentioning here a break. So if this condition is satisfied, that the absolute value of the difference of the two log likelihoods in any two step is less than 0.001, then we stop. And then we say that the final value of LLTM1, that's the log likelihood of the previous step, is equal to the log likelihood of the next step. Finally, the function returns the computed value of the mean and the variance. So pardon me, because SIT is the variance. Initially I said that it's the standard deviation, but it's actually the variance that's being calculated. So standard deviation is nothing but square root of the variance. Now to run in, we can draw a sample and assign some missing values. For that we set the seed at any number. Here we have set it at 1, 2, 3, 4, and then we generate a x or a vector from unknown. So it's randomly chosen. So a vector of 20 observations from mean 5 and ST1, and then we make the last 5 observations to be NA. So x 16 to 20 is NA. So if we print x, we would get what is the values of x. Once we have the values of x, we can find the initial values. Now purposefully I am taking the initial values as the observed mean and variance. So now my initial value of the mean comes out to be 4.662 and the variance comes out to be 0.7625157. Note that these initial values are nothing but the observed sample mean and the observed sample variance. So, this is equivalent to doing a complete case analysis for the initial values, and then we call the function em.norm and pass on the x values and the two initial values, and we get that these values are 4.6627. So, it converges immediately with 4.6627 as the initial value, estimated initial value, and 0.7625157 as the estimated value of the variance. And note that this is exactly equal to what we had got in our initial values, or we can think in this way that this is exactly equal to the estimates obtained from complete case analysis. See, the convergence is immediate because the explicit maximum likelihood estimates for the whole data are those based on complete case and ignoring the missing data mechanism, and we use them for the initial estimate. So, there was no repetition at all. It converged in the first iteration itself. But to see what the actual iterations are, we can change the values, initial values. So, we can change the initial value of the mean to say arbitrarily to 1 and the variance to be 0.1, and these are arbitrary values. So, we can take any value for it, and now we call em.norm x 1 and 0.1. So, that means we are again calling this function, but this time providing some arbitrary starting value, and once we run the code we see the output. So, it starts at 3.747, and so that is the initial mean value, and then goes on and on for the until convergence. So, at convergence it is 4.662689 and 0.7625643. Now, see that because we had not given the exact initial value, so if we once again compute what is the mean and the variance from the observed data, we see that it is more or less same up to 3 decimal places for the mean, and for the variance it is same up to 4 decimal places, indicating that EM is a very effective algorithm in this sort of situations. In our previous class, we had an exposition to what the EM algorithm is. In today's class, we did an R function that implements the EM algorithm in context to the univariate normal data. Now, the EM algorithm has 3 steps. So, we implemented all the 3 steps, namely the expectation step, the maximization step and the updation step of the parameters. We used a function, we wrote a function based on these 3 steps, and then we iterated these 3 steps until convergence. The initial values were initially taken to be the complete case values, and for a univariate normal distribution with missing data, the EM algorithm matches exactly with the complete case analysis or the estimates obtained from the complete case analysis. But we also showed that if we change the initial values, then there is an iteration happening and the EM algorithm converges more or less towards the complete case analysis values. In our subsequent sessions, we would be talking about the properties of EM algorithm. So, what are the properties of EM algorithm that makes it work in context to a missing data? Also, we would extend the EM algorithm in terms of a mixture distribution problem, and we would analyze the old faithful geyser data, which is a data set in R, and see how we can apply EM algorithm for a mixture modeling problem, where we need to estimate the parameters.